Okay, in our previous video on differentiating y equals x squared, we saw this. Now, formally in maths, we call this a limit as h approaches 0. So let's try and make that language a bit more precise, since it's obviously quite important. What does it mean when we use that word limit? Actually, I think the most familiar context we've already met these guys in, just without the language, is when dealing with asymptotes, like for the hyperbola y equals 1 over x. We would have used language like as x goes to infinity, 1 over x goes to 0. And that's essentially what a limit is. We may as well write limit as x goes to infinity of 1 over x equals 0. Now, does x ever physically reach infinity? Well, no, that wouldn't make any sense, right? And does y ever physically reach 0? Well, actually, we don't care. It can, or it couldn't, we don't really care, so long as it's getting closer and staying closer and closer to 0. We really do not care if it actually hits it or not. Okay, so let's explore this idea a little more. What does it mean to say that the limit as x goes to infinity of 1 over x is 0? Here's where the language of what we did in the previous video can come back. While it doesn't make sense to say x ever reaches infinity, we can pretend we're sending x towards infinity, and all that means is x is getting bigger and bigger and bigger. So let's start with, say, x equals 2 or something. That gives us y equals 1 over 2, which is, of course, half. So we can send x all the way down to maybe 10 now, or maybe even 20. And at this point, you really can't see the graph that clearly anymore, but we could go even all the way to 50 or go to 100. I think you get the point. We can keep going forever. And the question we're trying to answer is, as we do this, what's happening to the y value? And I'm sure you already knew, and you can see now, it's getting closer and closer and closer to 0. Okay, and what that means is I can literally send us as close as we like to y equals 0 by simply moving far enough across, by increasing x to a sufficiently large number. So right now we're 0.01 away from 0, but if you want, we can, for example, halve the distance by flying all the way to x equals 200. And so you get the point, right? We can get as close to the number 0 as we like by sending the x value far enough across. And that's what it means for the limit as x goes to infinity of 1 over x to be 0. Now, hopefully it's clear that such limits don't always exist for every single function. So let's say we take a sine wave instead. That just bounces between -1 and 1 forever. So no matter how far we send the x, the y value isn't getting closer to any fixed number. It just keeps bouncing around forever between -1 and 1, so there is no sensible number we can say it's always getting closer and closer and closer to. Okay, so we'd say that the limit as x goes to infinity of sine x just doesn't exist. Okay, so that deals with limits to infinity, which again might have actually been quite a familiar idea to you, even if it wasn't written this way in the past. Okay, so what about limits to a point? Right, like when we sent h towards 0 last time. To illustrate this, we're going to use the graph of sine x and also just the straight line y equals x, and we're going to ask for the limit of, actually not either of these things, we're going to ask for the limit of sine x over x, the quotient of them, as x is sent towards 0. Okay, just a disclaimer here, we will not be proving our answer rigorously. We're literally just going to illustrate what's happening on the graph. It does belong in maybe a different topic to deal with this properly, and we might treat that in a separate video later on. So hopefully it's clear that just substituting x equals 0 is not what we're doing here. Because if we tried that, it'd just be 0 divided by 0, which is all kinds of nonsense. But what we can do is start from some non-zero x value, which is going to give us two numbers we can divide. So we've picked a point where sine x is 1, so x is pi on 2, so like 1.57 or so. And these are two numbers we can divide, giving 0.63662 or whatever. Okay, then we can start sending the x closer to 0. So now it's like 0.9. And as we get real close, the value of sine x over x is now like 0.999583, and you can probably sense it's heading towards the number 1. And in fact, by sending x close enough to 0, we can make it so that my computer, which is calculating things to 6 decimal places, literally cannot tell the two numbers apart anymore. And so we can see that by sending x closer to 0, we can make sine x over x get as close as we like to the number 1. And so we would say the limit as x goes to 0 of sine x over x equals 1. It means that when x gets closer and closer to 0, the value of sine x over x gets closer and closer to 1, okay? So, quick note here, for the limit to exist and equal 1, we actually need it to get closer and closer to 1 as x gets closer and closer to 0 from all directions. So supposedly we can't just slide it in from the right, we're meant to slide it in from the left as well and check that it agrees, which it does. And that's really the point of a limit. It tells us not to care about what happens at some point. Indeed, for our function sine x over x, we literally cannot put x equals 0 or the whole thing breaks. Rather, it tells us to look at what's happening in a tiny little neighborhood around x equals 0. And it asks what's happening to our function as we send the x value closer and closer to 0 without ever touching it. Okay, so we'll leave it here for now. In a later video, we'll look at actually calculating these limits, which often isn't really as conceptually difficult, but that's all for now. See you around.